everyone. Welcome to Intro to Machine Learning. This is a workshop tailored for you guys to get hands-on ready with machine learning, and you'll learn some cool stuff about how machines actually learn. There will be a little bit of math, but don't let that scare you because I promise you it's not as bad as it sounds. All right, here's the workshop agenda, if it allows me. Okay. So we're going to do some pretty much just beginner stuff like introduction to neural networks, some activation functions, layers, and then we'll actually code a neural network. And by that I mean you guys will watch as I go over each line. And don't worry about copying down the code because I promise you it will be posted later. Yeah. What you looking at me like that? Okay. So first of all, we're going to get ready to the difference between artificial intelligence, machine learning, and deep learning. Pretty much, when you think of artificial intelligence, you might think, ooh, ChatGPT, ooh, agent. Those are subsets. AI is pretty much it's just a machine trying to copy human intelligence. An example could be AI, like a term for AI could be like NLP, natural language processing, or computer vision. Those are just techniques, or those are stuff that we use to try to get machines to mimic intelligence. A subset of the way we actually achieve AI is we use this thing called ML, which is it sits inside artificial intelligence. That's how we achieve. This is how we use. These are the techniques we use to help achieve artificial intelligence. Example could be we use, let's say, canny edge detection to help. It's a way that helps machines classify how to detect edges. That's something we use. It's just a bunch of math, I promise you, but it's cool math, and that makes it cool. And deep learning is obviously a subset. So ML is huge. You guys, these are each of these are the fields you can specialize in for yourself. Today we're going to be writing a supervised learning model, which pretty much this is just an overview. There's three main types. There's unsupervised learning, supervised learning, and reinforcement learning. Supervised learning, they learn on pretty much labels of data. So that's where you have people who go in and they annotate data. They tell the machine if this is a cat or if this is a dog. We know what's the predicted value, and the machine takes those inputs and tries to predict an output. The easiest way to explain deep learning, anything machine learning, is you have inputs and you have an output, and anything in between that's for the machine to figure out. That's pretty much the idea behind machine learning. Unsupervised learning, that one learns without labeled data. So if it finds patterns in, let's say, data, it's going to try to cluster the data together, which ones are more similar, and it's used in you can see a bunch of different types of applications. For example, if you use Netflix or YouTube, they have a recommendation system that's largely based on clustering and a bunch of similar ensemble models, which are just smaller little models that you have. Okay, so now we want to get you, familiar with the data pipeline. Yay. This is from scraping to deployment, but we are only going to focus on the anything data below right here. So we're going to be working with, above the giant data block, the yellow one, that's all data science and data engineering stuff that we don't touch. Ew. We're going to be working with pretty much the train, test, split, model engineering, model evaluation, and we won't be packaging and deploying our model because money and cloud, you don't want to deploy that. But you can, if you get further into the ML field, you'll learn something called ML ops, which is how do you train a machine learning model and then distribute it to hundreds of millions of users. And pretty much, yeah, what we're working with is train test split. For supervised learning, we want to have train test split. Right here, this train test is pretty much, you're going to take a subset of your data. It's just a little chunk of it. It's a good rule is around 70 to 30. And you're going to train the model with that. So you're going to train the model. It's going to try to predict what you give it the train data, you give it the actual like values, and you give it the the labels for it. And based on what the values are, for example, there could be an image, and you're trying to predict something. Let's say you're trying to predict if it's a cat or a dog. This is the most basic example. So one part of the train test, the train will be image, the other one will be label. And the same goes for test, for test. So inside test will also be an image and a label. And there'll be pairs, if you guys took discrete. I'm taking it right now. So you're going to use the training to train the machine learning model. And then for later on, if you want to evaluate your model, you'll be using the test, which that'll pretty much, you'll test your model on unseen data. It hasn't trained on it, so it won't know anything. So it'll show your model's performance on unseen data. That's pretty much for that. Now we're going to get into model engineering and pretty much what an artificial neural network is. Hello. Artificial neural networks, they mimic the human brain. There was two scientists in the 1950s who tried to machine learning, like AI didn't start in like the 2010s. There's a whole history with the AI winters. But pretty much it started in the 1950s with two people trying to model the perceptron, which is the human brain. This is, according to them, how we learn. And they tried to mathematically model that to an equation, or a graph. And this is called the linear unit, which you'll see like this. That equation should look very familiar if you guys passed algebra. Pretty much any neural network runs on these things called linear layers. This is the linear unit. This is one part of the model. It's pretty much the most basic neural network you can take. So you have your incoming, your variable x right there. So this could be an image. In reality, these will be matrices, and you'll have a lot of matrices, which is why GPUs are so popular, because they perform matrix multiplication faster than, say, CPU, because they're single process. But you'll take your input and you'll multiply it by your weight. This will be randomly initialized. This will be any value. It could be -3, could be 4, could be, 62. But you'll pretty much multiply it by your weight. And then you'll have a bias. This bias pretty much shifts it around, which I'll show you visually what this looks like. Because, but first of all, we want to go over a quick example. So make sure you guys get it. Ready? Let's say we're trying to predict how many, given how many sugars, I don't know, this is a good example. Sugar, you input sugars, and you're trying to predict how many calories. So you take your sugars and you multiply it by 2.5 in this case, which is 5 times 2.5, and then you add your bias of 1, which is multiplied by 90, which is your weight, and it gives you 102.5. So yeah, this is what it looks like to visually maneuver your weights and your changing your weights. This is pretty much, if you took algebra, you should know this. What is changing W? Just move this around. For example, these are your data points. I don't know if this is visible, but these are on there is your data points, and you're pretty much maneuvering. That's changing your bias, your B, shifts it up and down the graph, like your y-intercept. But let's say not all data is not linear, because if all data was linear, we would be having a fun time not inventing all these crazy AI architectures. But sadly, this is unfortunate. Data is not linear. For example, what if your data looks like this? Or in ungodly cases, that right there. We introduced something called activation functions right here. So linear layers can never move from planes. Without these functions, they will never learn nonlinear relationships. And in order to like fit the curve, we use these functions to actually learn. So you can see right here, we took our function right here, your y equals mx plus b. We wrapped it around a function h. So that represents our activation function. There's a bunch of different varieties of activation functions. Linear is apparently, actually I know that activation function. But for example, sigmoid, you want to try to squeeze the values between 0 and 1. There's ReLU, which is very popular. And you'll most likely will be using it today because how popular it is. And there's also TAN right there. All these activation functions have different different use cases. And for example, let's say you're doing some binary classification. Is it spam or not? You're going to most likely be using sigmoid because it has it outputs, if it's closer to, like, let's say 0 is not spam and 1 is spam, it's going to be between there. So that's a activation function that you'll most likely be using. But the real question is, so we've gone through how data propagates through them, but the real question is, how do neural networks learn? Like, what makes them learn? So in addition to training data and our architecture, we need 2 more things, and these ones are very fun. We need a loss function, or if you might have heard it referred to as a criterion, which no one else refers to that. Please do not refer to it like that. It's a loss function. Right here, loss function, and then we also need something called an optimizer to pretty much change the weights of the model. So if we go back here, we want to change these bad boys W to get a better result. So we introduce the loss function. This loss function will change depending on your task. For example, if you're doing binary classification is easiest, you'll be using a binary cross entropy or some other binary functions. Or if you're doing like you're doing categorical data and you need to classify something, you'll be working with loss functions that pretty much will predict the value. But for example, if you're doing something with regression, we use mean squared error, mean absolute error. It depends on your task. But right here, so you guys, I'm sure, have seen this function. If you guys have took stats, this is just mean squared error. So what do we do now? We have an equation to, so we have this equation back here that predicts a value, right? So what do? What should we do? What we should do is we should place it right here. So what do we do once we place it? Voila, we have our new equation, this shouldn't scare you. It's just you put in weights, you put in a bias, and then you calculate the mean squared error of that. And this equation right here, that's just a linear unit. There's no activation function because the example I'm doing for is linear, is a regression only, and pretty much the loss function measures the error between your target's true values and the model's predicted values. So it pretty much just tells you how wrong your model is. So the lower the model, or the lower the error, the better the model is doing. Or not always, but most of the time, the lower the error, you want your loss function to go down and not up, because then your model will be machine unlearning. So yeah, that's pretty much during training, the model will use the loss function to guide itself to find the right value, the correct values in pretty much the landscape of loss. It's weird, but you can represent that function in n dimensions, but it's really cool. That's more later on. It's pretty cool. It shows if you ever see actually you'll see that right now. So I just realized I forgot I had this slide. This is the optimizer. I forgot I had this visualization. This equation might look scary if you guys haven't taken Calc 3. I think that's when they introduced the gradient. This pretty much just tells you the, this tells you the derivative. I hope you guys have taken Calc 1 in each direction, pretty much. There's also, so up here what you're looking at is, this is the loss function as a plane, or as a, surface of the loss function. So if you take the potential weights and biases of every single point and plot it, this is what you get. So you want your loss function to go down. This equation here is for stochastic gradient descent. This is your model. This is your loss function here. And this, I think nom, I don't remember my Greek symbols. This is, I think, nom, not this is namma. This is eta, I think. This represents your learning rate, which pretty much tells your model how far you want to go down, or how fast you want to go down. Because go too fast and you will overswing and you won't be able to correct. So you want your model to slowly think of a ball rolling down the hill. You want it to just casually like enter this spot. But there's a problem with stochastic gradient descent, and it'll get stuck in local minimums. Like up there, you'll see the ball gets stuck at a local minimum, which there's different types of optimizers to help. There's been countless optimizers introduced to try to combat that solution. An example, and probably the one that we will be using today, is Atom. He was introduced, I think, in maybe 2012, 2015, somewhere in that time frame. That adds momentum. So the best way I can explain the optimizer is just think of the ball rolling down the hill, and you want to get to the lowest point. I should have also mentioned in the formula that if you took Calc 3, the gradient goes to, it points in the rate of greatest ascension, and that's why we have a negative in front of it, because we want to go down the fastest. So it's gradient descent. So now our equation, and stick with me, this isn't bad, I promise, is this. I promise you it's not as bad. Okay, I promise I'll explain it. So this right here, this first equation on the, let's see if I can, oh, that's actually so sick. I actually didn't realize I have a pointer. This equation right here, all we did was took the derivative. That's all happened with respect to W. This is a partial derivative in respect to W. This will tell the model, how W will change with respect to J. Like if you shift around W, what will happen to J? Will the loss function get higher? Will it get lower? So, and the same is this is the exact same equation, just with respect to B. And this will pretty much tell you, these two equations will tell you if you toggle around W and B, how will the loss function be affected? You know, because we want it to go higher. We do not want our loss function to go higher. We want our loss function to go lower. And this is what happens when we plug in the formula. This is your stochastic gradient descent formula right here that got plugged in right here. You see these on the bottom. So and here's a good example of how it's going down. So you see we have all these data points that we're slowly sampling one by one. If the GIF will reset, thank you. You can see our training loss is continually going down as we add more batches. So yes, as the batches increase, our weights and bias, they change with respect. So this means the model is learning. I promise it's just a bunch of stats and statistics. So now, if you guys actually want to go into the world of AI/ML, I give you two paths. PyTorch or TensorFlow. This is pick your poison, pretty much. I will give you some advice. If you truly want to go into AI/ML, and you want to actually learn what's happening, go with PyTorch, because this one, it's a lot more hands-on. It's a lot more dirty. You're working with actually like, you're doing everything manually, but that lets you train. That lets you pretty much help. Create your custom models. It also has something called a directed acyclic graph, which means the PyTorches, it computes on the fly as you add more operations. TensorFlow. Let's say you don't want to specialize in AI ML. You just want to stick your toes in and just enjoy your time right now. What I would recommend you would do is you should go with TensorFlow, because TensorFlow supports more production. It's more used in production because it supports a wide range of a wide ecosystem. It was developed by Google. And it also supports TensorFlow Lite. So if you guys want to train a model on Arduino, I don't know why you would, but God knows, not help me. And there's also supports TensorFlow JS. If you ever want to do machine learning in your browser, I don't know why you would. That's about it. But this is you pick your poison. You will be able to learn. If you truly want to learn PyTorch, it's also good for research. Most research labs, like in my 2 research labs, we use PyTorch because it's more used in research papers. If you guys know ChatGPT, it was trained on PyTorch primarily because most also academic papers are supported with PyTorch. So research, and also a bunch of companies use it. You can do your research for which company that you're trying to go for and which framework they use, and you can decide. And TensorFlow, this one's it's older, but it's used in production systems as well. Mostly, that's about it. So industry versus some research and maybe a little bit of industry. So now let's do some cool training stuff, right? Okay. I see you guys excited. So I want to tell you guys, how do you think computers see images? I want to hear some answers. How do you guys think a computer sees an image? Promise there's no answers and I don't bite. Or there's no wrong answers and I don't bite.
It builds an array or something.
You're on the right track. A computer sees an image as, okay, whatever. Chris, go on.
Is it, I don't know, like when they see a picture, they like minimize it to like embeddings or like, I don't know, pixels? Something like that.
Interesting. But it's sort of close. Pretty much, a image is a 3D array. You can think of it like that. He was right. Chris, you were somewhat-ish, right? Pretty much, computers see images as 3D arrays. So you guys remember your 2D arrays? Remember those from CS, I think actually Intro to C? Or maybe CS1, I don't know. CS1. Pretty much you take your 2D array and you stack them on top of each other. But each array represents a different value, red, green, and blue. In reality, this will be a 4x4 pixel, or a 4x4 image, which this will be absolutely nothing. Like you won't be able to understand it. But a good example here is this. We have this cat image. Actually, this one's very saturated. I don't like that. But we have this cat image right here. You can see that it's broken down into 28 by 28. That's actually really good for an image.
Understand what I said? I said pixels, bro.
No, but yeah, each of these represents, you can see the red, green, and blue. Pretty much these are all arrays, and they're stacked like this, which you can see right here. If you ever have reason to use a 4x4 pixel, I guess, or a 4x4 image, don't ask me. That's pretty much how images are seen in computers. That's a little fun fact, which you actually, if you do try to train your own model, which I will point you in some resources later on, you guys want to train your own model and do some cool stuff with it, I'll point you in the next direction. So we're going to be training one called, using something called the MNIST dataset. Very basic. If you ever, I don't know, even touched an atom into the machine learning pool, you've probably heard of MNIST. It's this data set right here. We're going to be training one to predict numbers. Yay! The images of numbers, yeah. And as you can see, they're grayscale. So they actually won't be red, green, and blue. They'll just have one color channel. They'll have one color channel. And now, I think this will allow me to do this. You don't have to copy down the code because I'm going to send it somewhere, I promise. Okay, how do I get my screen across? Okay. I'm gonna be zooming. I'm gonna step by step. This is completely so. We're gonna be using TensorFlow, and we're gonna be using Matplotlib and NumPy. These pretty much NumPy. This is how you manipulate tensors, which are stuff you use to train the machine learning models. And Matplotlib just lets me see the cool and pretty images. So this, if you look at the TensorFlow documentation, they have this MNIST. They have MNIST built right into TensorFlow. So if you guys want, what is it? You guys can try. I'm going this like I'm just try not to copy the code, or try to understand the concept of what's happening. So right now we are loading the data. This is data loading. Like this. In reality, this could be a CSV file for all. What is it for all it is? Or this could be images of cats and dogs. Then we turn the data that we have loaded. Actually, we haven't loaded it yet. That's what this load data function is for. We load it into two tuples, which this right here is test. Remember from our previous image, we have test. And this right here is train. And this xtrain contains the images, while ytrain contains the labels. So I'll show you guys an example later on in a minute. And this contains the data that we will be testing our model. The model will not see this data until after, until we start evaluating it. Then we want to normalize pretty much. You don't want your, we divide it by 255 because pixels go from 0 to 255 per chance. And we convert it to a float 32 because you don't want your pixels to be integers. That would be interesting if they were. Then these images are 28 by 28 pixels, which I'll show you more visually. And we just reshape them to add an extra dimension. Here, let me just scroll down real quick. Boom. So this right here is how this is how our xtrain or xtest looks like. Right now it's just an image. And I will show you up here, pretty much you'll be working with these things a lot, these dot shapes. I want to this conceptually wrap it around your head, that this just represents how much like your tensor is shaped. For example, 60,000 28 by 28 by 1. This TensorFlow uses the dimension of batch first, which is surprisingly not with TensorFlow. They use batch last, I believe. Or no, they use PyTorch uses batch last. TensorFlow uses batch first. So this batch represents how many images there are. This width right here. This is the width and height of your image, and channels. This is your RGB right here, red, green, blue. This is if it was a proper image, instead of the one at the end, it would be 3. So I just want you guys. This is. Let me actually. So in this example, right here, this would be a. Actually, let me open up notes real quick. This is actually tough. This is for, oh my god, this is for our old workshop. There's notes in here. Oh, that's actually so sick. But pretty much, this image right here would be a 1 by 4 by 4 by 3. Or if you learn anything from math, it'll be a 4 by 4 by 3. This right here, these first two values represent the width. Was it the width and the height? And this last one is the color of the channels. So pretty much you can think of adding on an extra dimension. So, for example, if you have an array, your array has 1, 2, 3, 4. The shape of that array would be 4, like this. And then you add in a 2D array, and you'll get so on. You'll add more dimensions, pretty much. Each of those is an extra dimension, and that's why we have. We're working with 6,000 images because images are 3D tensors. So we're working with 60,000 3D tensors, and then our test shape or our test shape right here. This is going to be a lot less because primarily, yeah, I said, well, like we said, we want a 70-30 split. If you can go away from that. You can do a 60-40 split of training test data, or you could do 80-20. Just don't do like 90-10 because then you'll have barely any images left to test on. So we first reshape it, and then we do something called one hot encoding, which pretty much means this is let me explain it to you. This pretty much turns we have a range, right? So we're predicting our values from there's 0 to 9 because we don't have 10, we don't have double digits. What we're pretty much doing is we're creating if you guys have used permutations in CS1, this is just for CS1 folks, because I know you guys, Ahmed makes you do the used array. Pretty much you set all the values in that array equal to 0 except the one you're working with. So for example, this one is 7 right here. So if we go up, we match each of these. You'll find that this one corresponds to the 7 spot. So pretty much, yeah. Let's say we can actually. I think is my collab on? Okay, collab. Another good fun fact. I'll show you if you guys want to. You guys can learn using Google Colab, because Google Colab is where most ML people have access to very powerful GPUs and data sets, especially with using Hugging Face. Because with Google Colab you have access to. I'll show you how to get all these for free. You have with just the Pro version, or without the Pro version, you have access to a GPU and a TPU, which is a tensor processing unit, which means they're specifically designed to run tensor operations. These are by Google, by the way, too. And with the Pro version, which I will show you how to get for free, wink, wink, that's why you should stick around. You'll get access to all these GPUs, like the H100 and the A100, which you'll have access to, which I actually can show later on. Pretty much right here, I'm not going to turn on because it's not too bad. So pretty much we one hot encode them, which pretty much you'll learn a bunch of different data preprocessing techniques for machine learning models. This is just one of them. It's called one hot encoding right here. It is there you go. It's a train test split. But if we choose, let's say this is actually really interesting. 6 right here. 6 add. Pretty much right here, you can see that all the other values there's every single value but 1 is off. So this represents the 6th value. So yeah, these zeros are just these values up here. So they're off. They tell the model that, hey, this image right here represents a 6. That's why it's in. That's why it has that one on. Okay. What is that? And now we're gonna train something called a. Oh yeah.
What if you turn 2 on?
Which one? Turn 2?
No, like 2 at the same time.
Like the one hot encoding doesn't do that. There is some. What is it? That's why it's called one hot encoding. It's primarily used to, let's say you're working with like a cat and dog, you can switch or you're working with multiple classes, let's say. So let's say, for example, in this one, yeah, it's 1, 2, 3, 4, but let's say you're working with something that uses multiple classes, like is this a image, is this a cat, dog, rabbit, stuff like that. You can use one hot encoding like this to train it. Pretty much think of it as, remember binary? You have 0 and 1, you can add another 2, 3, 4, and you can take, you have multiple classes pretty much. So it's the more type of data, like the more different types of data also require different architectures and more data preprocessing techniques, which by the way, if you guys want to, a good way to learn this is on Kaggle, which I'll show you later. It'll show you how to work with different types of data, tabular, if you're working with images, if you're working with, for example, data over time. That's a whole another architecture, which brings you into LSTMs and GRUs and a bunch of other fancy architectures the machine learning models have. Right now we're keeping it simple. We're starting with a DNN, or a dense neural network. What this means is, do you guys remember this linear unit that we have back here? Wow, thank you, Canva. we have this can right here. We're gonna add a lot of these, and we're gonna give them more a layer. So that's why when you think of a neural network, you most likely think of this image right here. You most likely think of this. This right here is a DNN, or yeah, pretty much. It's a bunch of linear layers combined. So right here you have your input layer. This could be the values of your image, and this right here could be this is your output layer. Everything in between, that's for the model to figure out. I promise. You don't have to tell it to turn on that way. It'll figure it out by itself. Okay, so that's pretty much what's happening. So now we're going to define a DNN, which is pretty much was what we saw earlier. So there's a bunch of different types of models, but the primarily one we use is sequential. This means that data follows layer by layer. It sounds boring to us, but it's cool. So pretty much it means your data will get passed through this, then it'll get passed through this, and then finally it'll get passed through this. Your data just follows a specific pattern. So we flatten our 28 by 28 image. We pretty much flatten it to a 1D array. So you guys know that just means it's going to become one array, one long 28 by 28 array. And then we introduce a dense layer, which is your linear layer, of 128. So that means there's 128 of these bad boys in the model. And each of them are performing a linear task. And we're going to finally apply a ReLU activation function, and that pretty much just makes it non-linear, because we have those things, those fun stuff. And then we're predicting 10 classes, 0 to 10. So your last layer is how the data will be output. We want to predict 10 classes because we have, we have data going from, pretty much the last layer will always be the number of classes you want. How many things are you predicting? We're predicting, is it a probability between 10 things? And that's why we use the softmax function, which this pretty much creates a probability distribution of which number is it most likely to be. It's big words. That's very big words. And then we finally what we do right here is we compile the model, we give it an optimizer, we give it a loss function. We're looking for accuracy, we're trying to make sure it's accurate. And we're also looking at you can also do model summary to check out your model. And then finally, we train the bad boy. We give it the validation, we give it how many epochs, this is how many times it'll feed the data into the model to predict it. And verbose 1 means we'll get to see it train. So let's train this model, and I can't see anything. Okay, thank you. Okay, there we go. This one's very saturated. But you can see right here the DNN is training. It's pretty much you can see its accuracy and loss are going down. Hopefully they are. Actually, yeah, they are. Which we'll see it plotted. But pretty much what it's doing right now is it's feeding this data into a bunch of into the input layers, and then it's trying to predict based on the pixel values what's happening. And that's pretty much what it's doing. And you can also see the accuracy. Right now it's 99 point, damn, that's actually really good. For DNN, surprisingly. But pretty much you can also see its validation loss. So this is right here, this is the test. So you can see it only scored 97 on the testing data. So that means, we should try to get our model to be better. So to show you that different types of architectures are better for different types of data, we're going to be using something called a convolutional neural network, or a CNN, which I don't know if you guys have heard of. So it's legit the same thing, a sequential convolution and a few other layers, and we pass it through the model here, and then we're going to, it's genuinely the same thing, except we're performing a little more computations. So you can see here, this is actually the summary of, this is how data will flow through your model right here. And now you can see it's training right here, the CNN model. And while it's training, if you guys have any other questions, I'm free to, I promise. But this is pretty much, this one's a lot more computationally expensive, pretty much. because you're performing convolutions, which is something that's like, I don't know if they cover it. I don't know if any of you guys know it, but you guys can research convolutions. They're pretty much, I don't know if I can find like a YouTube video. I don't know. But this is just a different type of architecture. And you can see immediately it got better results than our DNN model, which I just want to show you that different model architectures are better for different types of data. And I can go over, for example, if you're, fun fact, what is it while this is training? You know tabular data like CSV? That is actually deep neural networks are actually not the best type of ways to predict the data. You want to use some XGBoost or you want to use AdaBoost, which are different types of machine learning models. They're not a neural network. They're built on top of decision trees, which I believe those are covered. I don't know. Pretty much, you can think of binary trees, but now they're decision. So they have to choose between a choice. Like is this data greater than 3? We move on to the decision tree. There's a bunch of different types of powerful machine learning algorithms. For example, if we're working with data over time, let's say we have stock data over time. You want to predict or let's say we're working with, let's say a housing prediction. You can use like housing data over time. You could use an LSTM, which this is specifically designed for data over time. These are just different architectures you can, which you'll most likely learn if you go into the world of AI ML. You'll get suited for different types of architectures for different type of data. And I'll actually show you a great place to learn all this stuff because this model or this is I'm touching like the bare bones. I promise you this world is fun. Oh my god, this thing is taking forever. This is why you guys need a GPU or a TPU. This is because it took a while to train 5 epochs. But yeah, it's more computationally expensive because you're doing convolutions, which is why we have the AI boom happened because they have something called GPUs, which accelerate computing by, a lot more than using a CPU would. Chris, do you have any questions over there?
Yeah, why me, bro? You got other people, man.
No, but okay. Anyone got questions? You can ask about like different types of data. You can ask if a part was confusing to you. I promise. I hope I did well. Yeah, you bum.
Do you use RoboFlow?
RoboFlow? Yeah, I've used RoboFlow.
What is it for?
It's more of like a data annotation. So if you have, there's different types of famous models, which if you get into the world of ML, you'll be working with a lot of, for example, a good computer vision one is YOLO, which is probably the one that you're talking about over there. Yeah, good boy. Pretty much, YOLO is these are free models, like people do something called transfer learning, which is actually a really cool technique. It's where you take a bigger model, let's say you take YOLO and then you chop off its head, pretty much. You chop off the classifier, the last layer, because that layer lets you, predict a bunch of different stuff. And you can actually retrain it you can add on your own head. That's pretty much the best way to explain transfer learning. Imagine you can take your head, give it to like a super buff guy, and you're able to pretty much do everything that he does and look like him. So pretty much, you can swipe older models. Like you can take better models and retrain it on what you want. You don't have to build an architecture from scratch. I promise you, you can swipe a model from online. And a good place is actually a lot of these models are actually built into a lot of these tools. For example, TensorFlow has a list of models that you can swipe, like such as MobileNet V2, EfficientNet. I know these models by heart because I'm a bum. And PyTorch also has these models built in, so you can swipe them and actually, use them for your own tool. You don't have to sit here manually typing right here. What is it? Conv2D. This is the number of filters. This is the kernel. This is the activation function, and your input images of 28 by 1. This here is really, really the peak of engineering over here. Yeah, you.
So I have one question and a quick follow-up.
Oh, yeah.
So basically, when you're talking about swiping models, you're not doing that, you're building a model right
Yeah,
now?
this is a model from scratch. Like I am writing the architect. Like this is all the model is. But if you swipe a real, like an actual model, they could be right here. You can see the actual parameters. This is only 250,000 almost 225,000 parameters that you can train. Different models, they could have like millions of parameters. And what you're pretty much doing is, imagine I swipe this model off online. What you do is you get rid of this layer right here. You can see that the output shape is a tensor of 10. This is the number of classes that we're predicting, right? 0 to 10. So you swipe off. Let's say you want to only predict 3 things. You can swipe this last piece right here. You can delete it, and then you add a dense layer of 3, which that predicts your 3 classes. It's genuinely like the best analogy is cutting off your own head and putting it on a better like body, I guess. I don't know.
Okay.
That sounds wrong, but that's pretty much what it is.
Do you think it's valuable to take the time to build these from scratch rather than just skipping it?
Yeah, you can. What is it? A lot of research nowadays, what they do is they take old models, for example, ResNet v2, and they try to build on top of that to try to find more efficient algorithms. So pretty much a lot of these AI research stuff is you take old model, and then you just tweak, like add one more layer or one more module, and you're like, okay, this model performed better than the old one. So let's publish a paper on that and call it a day.
Because this is such an early like science.
Yeah.
basically, so-
And now, what is it? If a lot of research papers also filled with RAG, which is retrieval augmented generation. If you guys want to know any more, but like if you read an AI research paper, I promise you it's all gonna be buzzwords. Like one of our research paper was RAG with knowledge graphs on using LLM personalization or some stuff like that. It was atrocious. It's just buzzword. But pretty much, it's pretty much a lot of these models that come out. They're built on top of old research. It's the same like with research. I don't know why I'm going on a tangent, but old research is built on new research is built on top of old research. Same way new models are built on top of old models, and your architecture is continually improving. So now we test our model. So you have right here, we have our DNN that we're testing. I think okay. We run our DNN model and we run our CNN model, and we can see right here. We're testing this on the test. Remember the little 2 boxes that were train test? We're testing this on test, and so you can see our CNN model performed a lot better on images. Honestly, you saw how quickly the DNN trained. For let's say if you're working with business or like for any type, you have to also think about how computationally expensive your model is versus the accuracy. You want to have like not a too bad trade-off, because let's say your model takes 10 hours to train versus one that takes 10 seconds, and they achieve relatively same results. You got to think, which one do I want? Do I want to like this one is only like 2% better, so it's not too bad. So it's you have to think about how computationally expensive your model is, and a bunch of stuff like that. And so now we can actually plot the training epochs and accuracy. So right here we see this is actually really, you can see the loss goes down. So pretty much what this is saying is, fun fact, your model, it learned. It didn't just forget everything. This is pretty much what it's saying. It's saying your model learned, and then also as your model accuracy is going up like that. So you always want your you want your loss functions to go like this. There's a bunch of different problems you can arise. Sometimes I've seen loss functions where they just randomly spike up. That means your gradient's exploding, and you want to use gradient clipping. You'll learn this stuff if you go into this field. I promise you, it's fun, and it's not all boring. But yeah, pretty much you have your test loss. Okay, what am I doing? Where's my mouse? Yo, I low-key cannot see my mouse. Okay, there we go. Pretty much you want your accuracy is going up and your loss is going down. Means your model is learning. So now we're done with this. And I'll give you guys some free tools to get ready. So we want to delete and disconnect from time. I'll get you guys some free resources to start up. So first of all, for Google Colab, as students, actually let me see, we have Colab for free because we're cool like that. So you have access to very powerful GPUs. For example, ignore the research paper. This is a model. Right here we have Colab Pro. So I have access. So we have access to a bunch of what is it? Okay, there you can go this way. We have access to a bunch of what is it? GPUs for free, and to sign up for it, let me actually see how you do this one again. I just remember it's just you do like Google Colab Pro pricing. And then you can just sign up with your, right here, no cost for students and educators. Abuse the shit out of this resources. I promise you, it's good. The other one, if you guys actually want to learn ML, go on Kaggle, because Kaggle is a perfect place to, get your data sets and your model. You can also have a bunch of models. So these data sets, let's say you want to do some, let's say you want to predict Grammy Award winner or whatever you want to do with Grammy Award winners. A lot of this data is already here for you, and you can just swipe it. And honestly, the best way to learn how to use data in this field is just play around. Just play around. Like you can work with right here, time series analysis. So this you could use this you can try to learn what type of AI fits time series analysis. Or let's say you want to do something with computer vision, because we're a computer vision school. Classification of skin diseases. Let's say you're a medical and you're a medical student and you want to enhance your portfolio. You can show that you can use machine learning to classify skin diseases, or let's say you're e-commerce. For some reason you want to predict men's clothing. Don't ask me. Just you can swipe this data. It'll probably be a bunch of images. Let's see here. Yeah, it's going to be a bunch of images right here that you can go to. But most of these actually have real images. For example, the most famous one right here is, I think, cat versus dog. This is actually the one that I started on. Let's see here. Is it here? Oh my God, it's not here. No. Yeah, but there's like face mask detection. These will probably be actually a bunch of images. Right here, you can see these. Oh, these are XML files. Dang, is nothing real in images anymore? This is so sad. Let me see here. Pumpkin seeds. Yeah, no. But a lot of these will actually will come with the images. This is free data. This is free data for you guys to experiment, to learn with, to do a bunch of different types of stuff that you want to do with it. You can do some natural language processing. You can do classification. You can do regression. You can swipe pre-trained models, and you can, 1 billion token data set for LLM. Swipe it, play around with it, see what you can find. I promise you, this is a really cool and growing field. So, what is it? That's the best way. My last piece of advice: just start playing. All right, thank you. That's it. If you guys have any questions, I'll be up here. Okay, let me stop recording. This thing is still recording, isn't it? Bro. Oh yeah. Oh, thank you.